we are doing something I have genuinely been excited to put together. We are going inside a CPU, and I mean literally inside in 3D to understand how floating point addition actually works. And I know floating point sounds like the kind of thing that lives on a whiteboard in a university lecture hall. But I promise you, by the time we are done here, you are going to see it animated stage by stage, and it is going to click in a way that no textbook ever made it click. We have got 7 scenes. We go from a raw CPU overview through all three pipeline stages: align, add, and normalize. Then we hit pipelining, data hazards, and finally push the thing to 3 gigahertz to see what max throughput actually looks like. Let's us get into it. All right. So right there is a styled CPU. That glowing block in the middle is the floating point unit or FPU. Its entire job to do maths on number with decimal points, coordinate physics values, neural network weights, all of it. Now we are is the thing about floating point numbers. They are not stored in a way integers are. Every floating point number has two parts: a mantissa, which holds the actual digits, and an exponent, which tells you the scale. Think of it like a scientific notation. Here, 1.1011 times uh, 2 raised to 4, and that is your CPU sees it. And the problem, the reason we cannot just slam two of these numbers together and add them is that if their exponents are different, their decimal points to do not line up, you are basically trying to add apples and oranges. So the hardware breaks the addition into three separate stages. And that is exactly what we are about to walk through. So, okay, stage one, alignment. And this is the step that most explain gloss over. But it is actually where floating point additions lives or dies. Our two operands are equals to 1.1011 times 2 to the power of 4, and uh, second number is 1.13 times 0 times 2 to the power of 3. Watch that data packet moving into the align stage right now. Uh, See the left panel. The CPU first compares the exponents. A has exponent 4 and B has exponent 3. They are different. So the hardware takes the smaller one, that is B, and right shifts its mantissa by the difference, which is 4 minus 3 equals 1. So 1.1300 gets shifted right by one position and becomes 0.100 times 2 to the power of 4. Same exponent now, binary points are lined up. One thing worth flagging, that right shift can drop bits of the right end of mantissa. Those lost bits are gone. That, that is where floating point rounding error actually comes from. It is not a bug in the code, it is physics. Also, look at the bottom of that panel. That is an IEEE 754-bit layout. Uh, one sign bit, 8 exponent bits, 23 mantissa bits. That is the full 32-bit package for a single precision float. So now we move on to stage 2, the actual addition. And honestly, look at that ALU overlay in the middle of the screen. That is a binary ripple carry header doing its thing live. Watch the Watch the carry bits. They cascade from right to left column by column. Exactly the way you were taught to carry in primary school, just in binary. So we are adding these two number, and the result come out as 1 point, 10.0111 times 2 of the power of 4. Now notice anything weird? There are two digits to the left of the binary point. That is an overflow. In normalized floating point format, you are only supposed to have exactly one non-zero digit before the point. So we cannot call this the final answer yet. The result needs to be cleaned up. What is that is what stage 3 for. Stage 3, normalization. This is where the hardware tides everything up and produce a proper IEEE 754 result. So we had 10.0 overflow detected. The hardware shifts the mantissa one place to the right and bumps the exponent up by 1 to compensate. So this number becomes 1.00111 times 2 to the power of 5. And look at that result there. That just appear. That is your final answer. Clean, normalized IEEE 754 compliant. And notice the bit file at the bottom panel is updated. New exponent value, new mantissa bits. That is the exact bit pattern your processor would store in register. So three stages: align, add, normalize. One correct floating point result, but there is the thing: we just add that sequentially, one operation at a time, and that is incredibly so slow for a modern processor. What if all three stages could be running simultaneously? That is exactly what pipelining does. Let's us see it. Okay, this is the moment. Look at the pipeline right now. There are instructions in all three stages at the same time. While the normalized stage is finishing result 1 and add stage is working on result 2. And the align stage has already started on result 3. That is three floating point addition happening in parallel. This is instruction level parallelism, and the hardware trick that makes it possible is those thin registers you can see between the stages. They let the output of each stage at the end of every clock cycle so each stage can work independently without waiting for the others. Now look at the matrix on the right. Without pipelining, we get one result every three clock cycles. That is 0.33 instruction per cycle. With the pipeline full, we are getting one result every single cycle. That is one IPC, a three times improvement in throughput. And that meaning diagram shows it perfectly. Three instructions staggered by one cycle each, all completing one after another like clockwork. Same hardware, same three stages, same clock speed, just better scheduling. That is the entire point of pipelining. But it is not always smooth sailing. Welcome to the pipeline stall, or as a hardware engineers call it, the bubble. So those faded wireframe boxes mixed in with the normal data packet, those are stalls, empty stalls, wasted cycles. This happens when one instruction depends on the result of the instruction right in front of it. Say instruction 2 needs the output of instruction 1, but instruction 1 has not finished the normalized stage yet. The pipeline cannot just make our result, it has to wait. So it inserts a bubble a blank slot that travels through all three stages doing absolutely nothing. And watch that happens to the IPC. It drops from 1 to 0.66. Throughput takes a hit. This is called a data hazard. And it is one of the classic problems in processors design. Modern CPUs solve it with techniques like forwarding, where the result is routed directly from one state to the next without waiting to return back to a register, and out of order execution, which reorders instruction to keep the pipeline full. But for now, we just want to see what happens when the pipeline is clear and running at full tilt. Let us push the clock. And here we go. High frequency mode, 3 gigahertz. Look at those registers flashing. Here is a deeper insight about pipelining that a lot of people miss. By splitting addition into three smaller hardware chunks, align, add, normalize. The slowest individual chunk is much faster than the whole thing was. And because the clock period only needs to be as long as the slowest single stage, you can run the entire thing at a much higher frequency. At 3 gigahertz, with the pipeline running clean and full, we are completing 3 billion floating point addition per second per plane. Modern CPUs and GPUs have many of these lanes running simultaneously. That is how you get hundreds of gigaflops from a single chip. Look at that throughput comparison chart. And that is a wrap on the floating point addition pipeline. Three stages: align, add, normalize. IEEE 754 under the hood, pipelining to get from 0.33 IPC to 3 gigahertz throughput. Data hazards and bubble when things get messy. If this landed well for you,